Good morning. Today we are moving on into quantum physics or quantum mechanics. So we've got a couple chapters, 37 and 38, kind of setting out the foundations of this. And we're going to need quantum physics or quantum mechanics to be able to describe things like atoms or the nucleus or molecules. How do these things behave? What we're going to find is we're going to take many of the concepts that we've already learned, concepts like energy and momentum. We're going to take many of those ideas, but we're going to find out that we have to view them differently when we're looking at atoms and molecules. And so let's get started. Let's see what quantum physics includes. First of all, there's a list of the topics, so I'm going to go through this. That's kind of traditional for us. Ooh, it's a lot of writing from our first slide here, but it's saying that one of the first establishment of quantum physics was the early 1900s, determining that light consisted of particles. Now, for 100 years, all through the 1800s, physicists, chemists had been establishing that stuff around us was made out of atoms and molecules. So those were nuclei and electrons. But now what happened in the early 1900s also is physicists realized, oh, light also consists of particles. And it's not just visible light, but light across the spectrum. Infrared, ultraviolet, gamma, radio, everything consists of photons. And so what researchers found, what they discovered through their experiments, is that the atoms and molecules, the stuff that we refer to as matter, is constantly interacting with photons, particles of light. And so what's happening all the time is objects are radiating photons, and then they're absorbing photons, and we can even talk about kind of an equilibrium between the absorption and the emission of photons. So photons can be created or they can be absorbed. And I think that's mostly what this is talking about here. It's saying that there is this creation of photons is referred to as thermal radiation. So photons get generated, these photons of light get sent out away from the object, and we can go in and measure and observe the properties of this thermal radiation. Now they talk about an object that absorbs and emits thermal radiation, light, photons, perfectly, and we'll talk more about what we mean by that, across the entire spectrum. So it doesn't favor one part of the spectrum over the other. It's able to radiate in the infrared and the radio and the visible. It's referred to as a black body, something that we can actually carry out experiments on. So here's kind of the idea. What researchers decided they could do is, let's first of all think in terms of a container with some gas molecules inside. Well, you got gas molecules inside some kind of container. What we have found back in thermodynamics is that not all of the molecules are moving at the same speed. They don't all have the same kinetic energy. It turns out that statistically, it's actually more likely that there's a distribution of kinetic energies that the molecules have. So at any given time, some of the molecules will have more kinetic energy, some will have less, and then during collisions, during interactions between the gas molecules, that energy and momentum is transferred back and forth. So we ended up with a distribution. We said that if we plot the kinetic energies of these molecules, what we found is at a particular temperature, what would happen is there would be kind of a most likely energy, and so that's the peak in this plot. The vertical axis here is keeping track of numbers of molecules that have a particular amount of energy. And so at a particular temperature, what you would find is that most of the molecules or most of the atoms have an energy in this range. Some of them just, by statistical chance, happen to have less energy at that particular instant, and some of the molecules would have more kinetic energy. And we found out, we discussed this back in thermodynamics, there's a pretty strict mathematical formula that shows statistically what would the most likely distribution look like. And when you get large numbers of particles, the statistical formulas work really well. You can go back and look in those chapters. There was something called the Maxwell-Boltzmann distribution that we discussed. So let's think of that in terms of photons. How would photons, how could we think about photons, particles of light, in the same fashion? And we could start with a container. Now the container could contain other molecules, gas molecules, or we could just empty the container out. We don't have to have any gas molecules in there, because the inside surfaces of the container, they're going to be radiating photons. So what researchers realized they could do is they could actually build these devices. They could build these hollow containers, and they could heat them up to different temperatures, and then they could open up, make a small opening in the container, and they could actually sample the light that was coming out from the container. And so the idea here is, if we heat this container up, that's going to allow it to reach some kind of an equilibrium. Now, what does equilibrium mean for a bunch of photons, a bunch of particles of light? Well, same as with the gas molecules, if we're looking at the collection of photons inside here, there could be photons with more energy or photons with less energy. It turns out that at higher temperatures, the molecules, or the atoms that make up the gas molecules inside, or the surface of the material, at higher temperatures, those are going to have more kinetic energy. There's going to be more energy of vibration in the nuclei moving back and forth. There's going to be more energy of translation and possibly rotation in the gas molecules. And as the surrounding molecules have more and more energy, they're going to tend to radiate photons with more energy. So what happens here is, if we look at numbers of photons being generated inside here as a function of photon energy for a given temperature, there's going to be, kind of a most likely energy that the photons would be radiated with. And then it becomes less likely to radiate photons of higher energy, and less likely to radiate photons of lower energy. Now, what happens as the temperature goes up? Well, if the temperature goes up for these gas molecules, then this graph shifts. The peak of the graph will shift to the right, and what that's indicating to us is that we now have more molecules that are at higher energies. The same thing happens with photons. So as the temperature of the surrounding materials increases, the energy of photons being produced tends to increase. Objects at higher temperatures produce photons of higher energy. Okay, and that's, feels, I hope, kind of intuitive as to what we would expect. Now, there are some important differences here. The gas molecules are what we consider to be conserved particles. Protons, neutrons, electrons, for the most part, end up being conserved. And that says that we have, we can think of this as a fixed number of gas molecules in the container. That's not true for the photons. So as we go to higher temperature, not only do we radiate more photons of higher energy, we radiate more photons, or the materials radiate more photons across the entire spectrum. So as the temperature goes up, these materials will just generate more and more photons, and the average energy of those photons will increase. So that's a nice comparison, I always feel like, because you guys are familiar with gas molecules, I'm guessing, and what their properties are. Okay, here's their graph of what's going on here. So here it's showing the photons, the thermal radiation curves for 3 different temperatures. Now, it's kind of traditional with light to use a horizontal axis that's in terms of wavelength, in terms of energy. And so that throws things off a little bit. It turns out that the wavelength of a photon of light is equal to h times c divided by the energy. Now H is what we call Planck's constant, and we're going to see that defined here in just a few more slides. C is the speed of light, and so hc divided by the energy of the photon gives us the wavelength. Now what that tells us then is that high energy photons have short wavelengths, and low energy photons have long wavelengths. And that means that on our graph, if we're looking in terms of increasing wavelength to the right, that means increasing energy is to the left. So here, the energies actually increase as we move towards the left side of this. And I think when you look at the graphs in the textbook and such, those are going to be geared in terms of wavelength. So again, the wavelength for these photons is going to be determined by how much energy the photons have, more specifically by how much momentum the photons have. And we looked at some of those properties in the last chapter. So let's see. So for us, let's say that we've got that container set up and we're sampling the light, the container we showed in the last slide, and we're running some experiments. We've got a container set up, we've heated the container up to 3,000 Kelvin, and what we're finding is that the light that's being generated at 3,000 Kelvin, the most likely wavelength is just below 1,000 nanometers. So nanometers, if we're looking at visible light or if we're looking at infrared or UV, typically we're going to be measuring those wavelengths in nanometers. So what it says is at 3,000 Kelvin, we're starting to get a significant number of photons generated in the visible part of the spectrum. But it's still the case that the bulk of the photons being generated and the bulk of the intensity of the energy that's being generated is in the infrared. Now what happens at 4,500 Kelvin? Well, across the entire spectrum, there are more photons being generated, and that means more intensity. If you remember, intensity is joules per second per square meter. So more energy is coming off that surface per area per second. And the photons on average have more energy now. Now we're getting to the point where a typical photon is actually in the visible part of the spectrum. It has enough energy that we would now classify it as visible. It's enough energy that it activates our retina. And then at 6,000 Kelvin, now 6,000 Kelvin, that's about the temperature of the surface material on the sun. And so at 6,000 Kelvin, now the peak wavelength, the wavelength that's being generated at the highest intensity, is now clearly into the visible part of the spectrum, kind of at the center, kind of in the yellow and the green part of the spectrum at that point. Okay, so now what they've done along with wavelength here, they've also included frequency, and we need to get a formula out here for frequency in terms of energy also. I think we have that coming up ahead. Here's how that graph works. So just to be clear about this, intensity is in terms of watts per square meter. This is what the graph looks like. Now what we're going to say is that if we take this graph and we split it into a bunch of very thin vertical bins, each one of those represents a certain amount of intensity within a particular range of wavelengths. Now if you're saying, oh, this looks kind of like my calculus class, you're right. You guys are not, the integrations that we look at in this chapter are here only, for us, they're here only so you can kind of see how this is being derived. So you guys are not required to do the integrations that are here. What you want to be able to do is work from the results. Now when we carry out the integrations here, what we find is, so I've highlighted the items that we want to be really clear on. So the wavelength of peak intensity, so this wavelength right here, where the graph peaks, is given by a constant divided by the temperature. And that constant, if we do a series of measurements, we can establish the value of that constant, and that constant is 2.90 millimeters times kelvins. So what this formula says is that as the temperature goes up, the peak wavelength gets shorter and shorter. Now, there's a second feature of this thermal radiation, of the black body radiation, and that is that the overall intensity, the combined intensity, now that would be integrating across this function, and that would be the area under the curve. So if we go back and we look at the area under the curve, notice that as we go from 3,000 Kelvin to 4,500 to 6,000, and notice they're drawing in some color for us here. The red is actually still in the infrared. 4,500 Kelvin, we've gone into the visible. It peaks in the orange part of the spectrum. And here at 6,000 Kelvin, it's peaking in the green part of the spectrum. So for those graphs, see how the area under the curve is getting larger and larger? And again, it's that feature that property that we talked about. As the temperature of the material goes up, the combined intensity of all the light being produced increases across the spectrum. We get more and more photons being generated, and on average, those photons are being generated at higher energies. Photons coming off have more and more energy individually. And that's what this is showing, is that the overall total intensity of light coming off that surface is given by what we call the Stefan-Boltzmann constant, 5.67 10 to the minus 8 watts per square meter per Kelvin to the fourth, and then we multiply that by temperature to the fourth. Now at this point I always stop and I think, oh, how often have I seen a formula with something to the fourth power in physics? And it hasn't shown up that much. So this is, we're saying if the temperature doubles, well, that doubling would get taken to the fourth power. That would be 16 times as much energy. And that's actually what we have in that graph. So if we go from the total intensity at 3,000 Kelvin, and then we double the absolute temperature. We've got to be working in terms of absolute temperatures here. So we're working on the Kelvin scale. 3,000 Kelvin to 6,000. That area under those curves, the one under the 6,000 Kelvin is 16 times greater. It's generating energy at 16 times the rate per area. So let's say, here's some numbers. They say let's try these formulas out. And let's look at the surface of the sun. So here we go. So here's the sun. The surface is at some temperature. There's an intensity of light coming off. So the sun's kind of an interesting case. Before we were talking about these containers that physicists could build and then sample the light being generated inside. The sun's kind of an open container. So gravity is holding all of the material of the sun together. So it's, the material is being held together. All of the atoms and molecules at the surface of the sun are generating light. Now, light's being generated throughout the entire volume of the sun, but it turns out that the light that's generated deeper gets reabsorbed before it can exit the sun. So the light that we see coming away from the sun, for the most part, has been generated in the outer layers. The outer, 100 kilometers or a couple hundred kilometers is where the light we see has been generated. Now, in those regions, the temperature is 5,800 Kelvin. So that's our measurements. By looking at the spectrum of light coming from the sun, we can determine what the temperature is. Nobody handed us something and said this is what the temperature of the sun is. We didn't get any thermometers up there. We're actually using our understanding from experiments done here on the surface of the Earth to be able to sample the light coming from the sun and be able to understand what the temperatures are there. So, so here we go. Here was that first formula. It says, let's go ahead and predict what the, this is it. So this is how we're going to determine this. So when we look at the sun, we find that its peak wavelength is pretty close to 500 nanometers. So kind of in the middle of the visible part of the spectrum. We've been saying the visible part of the spectrum runs from 400 nanometers to 700 nanometers in terms of wavelength. And so the peak wavelength for the sun is at 500 nanometers. If we plug that into the formula that we're going to be using, we can put in the wavelength, and that will tell us what the temperature is. So for a sample of gas molecules in the outer layers of the sun, of a star, where the peak wavelength is at 500 nanometers, we can put in, now this is that very same constant, but it went from being 2.90 to 2.9 million because we switched over to nanometers. For visible light, nanometers are going to be easier units to work in terms of. So this is that constant. And what it says is I can sample the light coming from the sun. I can see that the peak wavelength, the most intense, the wavelength at which the intensity reaches its highest value is at 500 nanometers. And that tells us the surface of the sun is at 5,800 kelvins. Okay, that's how we're determining that value. Now once we know the temperature, we can plug into the second formula and we can calculate an intensity at the surface of the sun. If we integrate across all possible wavelengths, and that number works out to be 64 million watts per square meter. So imagine going up to the surface of the sun. Here's 1 square meter, so a meter here, that's 1 square meter, and we put that down on the surface of the sun. And through that 1 square meter, and this applies to every square meter along the surface of the sun, there are 64 million joules coming out every second from just that 1 square meter. Okay. Now this is a number we can double check. So we can go back in now and we can go, okay, is this really going to work? Because the formulas that we have developed here on Earth in our labs, we're now applying this to the surface of the sun. We're predicting that the surface is at 5,800 kelvins, and that's predicting that the intensity is this 64 million watts per square meter. If that's true, we should be able to measure the intensity of the light coming from the sun, and it matches. So, all of these derivations that we've come up with, they work. Now, to figure out the total power, how much and at what rate is energy being radiated away from the sun, we would have to include the entire surface area. So we can take this intensity, which is, millions of watts per square meter, and multiply by the surface area. Surface area of a sphere is 4 pi r squared. Works out that the surface of the sun is at 6 times 10 to the 18th square meters. It says the total energy output, the rate of energy coming off the sun in terms of photons. Now this is just the photons. Turns out the sun is also radiating what we call neutrinos because of the nuclear reactions in the core. The neutrinos are carrying a significant amount of energy away. We'll talk more about those later in the course when we get to nuclear physics. And then, there's some number of electrons and protons and neutrons too that are ejected out into space. So, but this is the portion coming away due to the photons being radiated that have left the sun, left the material of the sun, and they're headed out through the solar system kind of on their own, radiating in all directions. 3.9, 10 to the 26th watts. So it's kind of fun to be able to take something like a star and calculate all of its properties. Now just for comparison, let's compare a star with a planet. Let's use Earth, why not? So let's say that the surface of the Earth is at 300 Kelvin. That's an easy number to write down. We could use the same formula that we've used for the sun, and we could determine, well, for an object at 300 Kelvin, what would be the wavelength of peak intensity that's being radiated away? And that works out to be 9,000, well, really close to 10,000 nanometers. 9,670 is the peak wavelength. Now, let's think about that. That's the Earth radiating photons away, right? So what's happening with a planet like Earth that's part of a star system. It's absorbing light from the star. So this sunlight is coming in, and we can do this. We'll try this on the next slide here. We can take the intensity of the light coming in and determine what's the rate of absorption of light, assuming that the Earth is perfectly absorbing across the spectrum. And then at what rate is light being radiated away, and at equilibrium those two will match. And so Earth is radiating light, photons, away, but they're primarily in the infrared. You know, we don't see the Earth's radiation because it's not in the visible part of the spectrum. The Earth is not radiating a significant amount of photons of light in the visible part of the spectrum. All right, so the intensity here that we, following the formulas, the intensity is 460 watts per square meter compared with 64 million. So those numbers are pretty different. If we multiply by the total surface area of the Earth, take the intensity, multiply by the area to get the power, Earth's radiating away photons which have a combined power of 2.34 10 to the 17th joules per second. So that's the rate at which energy is being carried away from Earth. Now, if Earth were just left to itself, the Earth would cool down as a result. But there's a nearby star which is radiating energy in, and what happens is, to a first approximation, the rate at which energy is coming in is going to match the rate at which it's leaving, and that's going to determine what the temperature of the planet is. If it's closer to the sun or closer to the star, this temperature will be higher. If it's farther away, the temperature will be lower. We'll see that we can go through, and well, here it is. So very next slide, here is a star. Here is the radius of the star, half its diameter. And then the starlight's coming in, it reaches a planet. And here's kind of that assumption we were saying. Let's imagine that the planet perfectly absorbs the light that's coming in. Now the light that's coming in is probably in the visible part of the spectrum. So all this light is coming in, it reaches the surface of the planet absorbs that, and then those atoms and molecules radiate a new set of photons away. So visible light energy photons coming in, typically infrared photons leaving. Now, and again, the first approximation here would be that the rate at which the energy is coming in is the rate at which it's leaving. And so what we can do is we can say at the surface of the star, the intensity coming off is the Stefan Boltzmann constant, sigma, times the surface temperature of the star to the fourth power. Now what happens with the total power is that as you get farther away from the star, the intensity drops off. The intensity of the light is going to drop off as we get farther and farther away. And in fact what we can say is that the total power radiated by the star, we can measure that at the surface, that's intensity times area, and then we can measure it again at the location of the planet. So little r represents the orbital radius of the planet. So we have these numbers for Earth, right? We know what the radius of the sun is, we know how far the sun is away from the Earth, center to center. It says that the intensity of light reaching the planet, the intensity of sunlight, is predicted to be sigma, t to the fourth, depends on the surface, or the radius of the star, and it depends on the distance to the planet. Now we're going to take that energy coming in, or that intensity of light, and we're going to say that for the planet, the power in matches the power out. We can write those formulas down. Now for the power in, the sunlight that's coming in, the planet represents a circular cross-section. So the planet is a circular cross-section, and so we're going to write that as pi r squared. So the light's coming in this way, exclusively from the star, but the light's radiating in all directions. And that's why for the light being radiated by the planet, we're using 4 pi r squared. For the light coming in, we're just using that circular cross-section of light. And this is the formula. Once everything cancels out, it says that the temperature of the planet to the fourth power equals the temperature of the star to the fourth power times the radius of the star squared divided by 4 times the distance between the planet and the star. Ooh, here's some planets we could try that out on. So, all right, what planets do we have here? This is Mercury, which actually looks a lot like the moon, and the moon's not all that much smaller. You know, if we scaled this down 30%, maybe 40%, you know, the moon's, we could just take a small picture of, take a picture of Mercury and scale it down, and it would, you know, it would pass kind of as kind of the moon. Anyway, so the moon's a good, you know, the moon's a good-sized object. And then this is Venus. So, and that's Earth, and you can go, wow, Venus is just about this. It's a little smaller, not much. And then this is Mars. And Mars, you know, is significantly smaller, but there are what we call the terrestrial planets, the inner planets of our solar system. You guys recognized Earth, right? So let's try this. Let's take this formula that we came up with for the planet temperature. Now we're going to start off by, what was it we needed to know here to use our formula? Okay, that's the formula, the one box down here. It looks like we need to know the radius of the star and the distance from the center of the star out to the center of the planet, and that will allow us to go in and predict, using this first level approximation, where the planet absorbs all the light coming in and then re-radiates its own light in the infrared. What it predicts is that Venus, which is 108 million kilometers from the sun, would be at a temperature of 329 Kelvin. Now that's a pretty high temperature to go survive on Venus, but it's not terribly hot, right? With some good air conditioning, maybe that would be something tolerable. Now that's the prediction for Venus, but what we observe is that the surface of Venus is actually at 740 kelvins, so that it didn't match at all. Why is that? And that's because Venus experiences what we consider to be a runaway greenhouse effect. So Venus's atmosphere, from very early on, contained an enormous amount of carbon dioxide, and that carbon dioxide is still present in the atmosphere. And the carbon dioxide allows a fair amount of the visible light to reach the surface, but it really slows down the process of radiating. So it's kind of like putting a blanket around the planet. What it does is it provides, that carbon dioxide provides a thermal layer that restricts the infrared being radiated away from the planet, so you can see what a very extreme runaway greenhouse effect due to carbon dioxide. Now for Earth, Earth's a little farther away. That's kind of the only thing we have to change in this formula. So Earth's a little farther away, and its temperature is predicted to be 279 Kelvin. Boy, that's not a bad approximation, is it? So this very simple approximation based on how light is radiated away from materials and what the distribution of light looks like predicts a temperature 279. That's pretty good. And for Mars, predicts Mars very well also. 228 Kelvin on the surface of Mars. So Venus is the real standout here. Now Earth also started out with a very large amount of carbon dioxide in its atmosphere, but Earth was at a little bit lower temperature, and so the water, Venus and Earth both started with a lot of water. On Venus, the water remained a vapor and eventually was lost from the atmosphere. Water is a very low molar mass compound, whereas Earth retained its water in its oceans, and the carbon dioxide could dissolve into the oceans. So when you think of rocks, you take a geology course, and there's, you know, sodium carbonate and potassium carbonate and all these different carbonates. Well, that's where a lot of Earth's carbon dioxide is. And then there's all of the calcium carbonate, the shells of different ocean life. So most of Earth's carbon dioxide now has been drawn in, has become part of the planet itself. It's no longer in the atmosphere. Venus, all of its CO2 is still in the atmosphere, and it experiences a runaway greenhouse effect. Okay, and that's why we're trying to, prevent our carbon dioxide levels from going higher. More carbon dioxide in the atmosphere means that it's more difficult for the for the infrared photons to leave the planet, and that increases the surface temperatures. Okay, here's another example. Here's another one with star color. It says that we have a star with a surface temperature of, that's a really high surface temperature. Remember, if we go back and look at the sun's surface temperature was 5,800. This one's at 32,500. What color would this star appear to be? And we're just using that formula again, so we can predict what wavelength will show up at peak intensity. So the wavelength of highest intensity, we can put in the constant A, divide through by that temperature. Ooh, this time the wavelength is 89 nanometers. Now that's a really short wavelength. That would be in the ultraviolet. So those photons would be much higher in energy that are being generated. But that's, I have the graph. I was thinking I have the graph backwards, but this is right. So if we look at, here's the visible part of the spectrum, right, being produced. And so it says that the peak of the intensity, this is another intensity graph, I needed to label the left side, it peaks in the ultraviolet, and that says that, the blue end of the spectrum, the blue and the violet end of the spectrum is going to be produced in larger number. Blue and violet photons are going to be produced in the highest number, so it's going to be a blue star. So we observe these types of stars, and they look blue. Okay, so here, this is a plot that takes us back to around the year 1900 or the late 1800s, when researchers, physicists, were trying to figure out why. Now this red line represents what observers were really observing. And these were some different predictions from different researchers at the time. And they just weren't able to start from kind of fundamental principles and derive the formula that we've been working from. And Max Planck, a German physicist, was able to come up with a mathematical expression that exactly matched the experiments. And the way he did it was this. It was a bit of a trick. Planck was just playing around with mathematical formulas and said, what principle or what assumption could I make that would lead to the observed sorts of intensity spectra that we're seeing in the labs? And the assumption he made was that the frequency of the light of different frequencies, was related to how much energy that particular light had. Now there's a constant in here, and this is now known as Planck's constant. By making this fairly simple assumption that the energy of the light was proportional to the frequency of the light, inversely proportional to the wavelength, Planck was able to derive a formula, start from very basic assumptions about the atoms and the molecules and how they radiate photons. And so now Einstein picked up on this. Albert Einstein said, what's going on here is that when you say that the frequency and the energy of the light are proportional to each other, what does that really mean? And Einstein said what it means is that light is made out of particles. That an individual particle of light has a certain amount of energy to it, and that the frequency of that light is proportional to how much energy it has. So Einstein came up with this interpretation and said, look, light's particles. And at that time you could say, well, we know that atoms and molecules are made out of particles, or that, let's step that back one more, that materials around us are made of atoms and molecules, and this all traces back to protons, neutrons, and electrons. And so what Einstein is saying here is light also is particles. And that means when materials radiate light or when they absorb light, it's particles radiating other particles, or particles absorbing these light particles is what's going on. So let's calculate some photon energies. So they're saying if we have a photon with a wavelength of 450 nanometers, so let's say I have a beam of light, and that beam of light, we measure the wavelength, and we find that all of the photons in that beam of light have a wavelength of 450 nanometers. Well, if the photons all have that wavelength, how much energy would that correspond to? Now, in the last chapter, in chapter 36, in relativity, we said that these two formulas are the fundamental energy formulas in nature. That special relativity tells us that this is how energy, mass, and momentum, and kinetic energy are all related. Now, another thing we said in relativity, in special relativity, was that special relativity says you don't have to have mass. Something can exist, you can have particles that have no mass, and that's not a prerequisite for them existing. So in the case of a massless particle, and all the evidence suggests that photons are massless. So we've done really careful measurements of photons. If they have any mass, it is really tiny. So we consider photons to be massless, and that says that, using the formulas from relativity, that the energy of a photon and the momentum of a photon and the kinetic energy of a photon are all the same number. Now, in reactions, energy gets conserved, momentum gets conserved independently. So even though these are all the same number, they still represent different quantities. Now that we have these relativity formulas and we're identifying properties of photons, in quantum physics, I'm going to say the fundamental formulas from quantum physics start out with the assumption for any particle. This applies not just for photons, but it applies for electrons, for protons, for neutrons, for what are called neutrinos that we'll see in a few chapters. The frequency of any particle is proportional to its energy. And the proportionality constant is, again, it's Planck's constant. There is this value of little h that Planck came up with, or he placed in his derivations. And so we now have to determine what is the value of Planck's constant, and that will allow us to take the energy of the photon and determine its frequency. For the wavelength is directly related to a particle's momentum. And so the wavelength is given by h divided by momentum. So let's try that with photons. So if I take this general formula from quantum physics formula is telling us what the wave properties are of a particle. So the wave properties are based on the particle's energy and the particle's momentum. The wavelength then is h over p. That's a general formula I can write down for anything. Now what we're going to do is, we're going to claim this as a shortcut. Back in chapter 36 with relativity, we found out if we added a factor of c, the speed of light, into some of our formulas, we could actually create shortcut formulas from that. So this is an example. I can take h over p. Now that could be written as hc over pc. Now up to here, that's a general formula, but now we're going to apply it to photons. For photons, pc is the same thing as the particle's energy. And so we can say that the energy can be directly related to wavelength for the photons. That gives us a formula which, again, I've highlighted here. So I mean, ideally, you would have kind of a general understanding of where these formulas are coming from. The most important item for us, the most important skill for us, for you, as a student in the course, is being able to work from these formulas. So being able to, if you're given a wavelength for a photon or another particle, how would we go about calculating its energy? If we were given its energy, how would we go about calculating a wavelength? So being able to work from the formulas that we've developed here. Now, it turns out that Planck's constant, I'm going to use that formula that we just came up with for our photons. Planck's constant in standard units is right here. That says h times c. This is h, that's Planck's constant, times c, the speed of light, or the space-time conversion factor. So I can take h times c, I can divide through by the wavelength that we were given in the problem. So this is an example that we were given. And this is the energy of one photon that has a wavelength of 450 nanometers. And this doesn't need to say nanometers. I need to get that canceled out. It's 10 to the minus 9 meters. I put the 10 to the minus 9 in, so I don't need the nano. I don't want both of those in there. I could drop the 10 to the minus 9 and keep the nano, or keep the 10 to the minus 9 and drop the nano. The energy of one of those photons would be 4.42, 10 to the minus 19 joules. Now it turns out there's a shortcut. Here's the shortcut that I'm claiming we can work from. Hc, I can take Planck's constant times the speed of light. I can convert into EV. Now again, we found out in last chapter, when we were looking at relativity, that when we're working with individual particles like electrons and protons and such, EVs are actually very handy energy units to be working in terms of. So I'll convert from joules into EV, and I'll convert from meters into nanometers, and Hc becomes 1,240 EV times nanometers. So what we've done is we've taken all these numbers with lots of scientific notation, and I hope simplified it into 1,240, 1240. The units now are EV and nanometers. And that, I'm going to claim, is going to let us do faster calculations. Here's another example. Here is a light bulb, and we're trying to calculate how many photons are coming out of this light bulb in a given amount of time. So let's take a look and see. Let's say that we have a 100-watt light bulb, and we're assuming that the bulb has an efficiency of 3%. It's saying 97% of the energy goes to heat. Okay, I've got some issues with this problem. So let's take a look and see. So here's one of those old-fashioned incandescent bulbs that we may have grown up with and maybe still have around somewhere. So here it's listed as 100 watts. I go to the store, it's listed as a 100-watt incandescent bulb. Has a filament inside, the filament just heats up. Now what we find is that only about 3% of that energy is going into visible light. And the other 97% it says is going into heat, but that's infrared, right? So it's still generating photons, it's just generating photons that we can't see. It's not lighting things up, but it's radiating infrared out into the room. Now what they've said is, I guess this is what we're going to say, what we're going to do is we're just going to ask how many visible photons are being generated by this bulb. It's generating, most of the photons being generated are going to be infrared photons, but we're interested in the visible photons. So let's think the red light has a wavelength of about 700 nanometers, blue light 400 nanometers. Now this is the new formula that we said we want to try out. We derived this on the page just before. And so it's saying that I can calculate the energy of the photon by taking Hc divided by the wavelength. If somebody gives me the wavelength, I can calculate the energy from that. And Hc, we showed, was equal to 1,240 eV nanometers. So I'll write that down. I'll divide through by the wavelength, 700 nanometers. Oh, look, the nanometers cancel. This is going to make the formulas, the calculations go so fast. I pick up my calculator, I enter 1,240 into my calculator, I enter 700, I take 1240 divided by 700, 1.77 EV. I had to do one division, and I'm there. I converted the 700 nanometers, and it's telling me that a photon of wavelength 700 nanometers has an energy of 1.77 EV. That's a red photon. If I go to the blue end, the far blue, this is really violet, but we refer to it as the blue end of the spectrum, 400 nanometers, I can take the 1240, divide by 400, again, one division, and that gives me 3.10 EV. There it is. I've taken the wavelength range of visible light and converted that into photon energies. So what I did was, now 3 watts would be 3 joules per second, right? And I converted those into EV. So as you can see, we're converting back and forth between EV and joules is going to show up from time to time. It did in this problem. So remember that conversion also. And it says that the light bulb is producing, in the visible part of the spectrum, 1.88 10 to the 9th EV of visible light every second. Well, I took kind of an average. I don't know if that's an average. Is it 2.5? I tried to take an average between 1.77 and 3.10. I said, okay, a typical visible energy photon has about 2.5 EV of energy. So I took the rate at which energy is visible light energy is coming out of my bulb, and said about 2.5 EV represents one individual photon, and it says that this bulb is producing 7.5 10 to the 18th visible energy photons every second. How many infrareds is it producing? Many, many more. Probably, many, many more. We'll leave it at that. Because 97% of the energy is coming out in terms of infrared. So that's it. We can, run some calculations and actually calculate numbers of photons being generated in a particular situation. So I think we're coming up on time to take a break here. I just wanted to, one more slide here, I think. Probably just one more. This was the intensity formula that Planck came up with. You can look at it as much, if you can spend whatever time you want to looking at this. We're not going to do anything directly with it. What that represents, if we go back to these graphs that we've been looking at, it's the red line in that graph. And if we go back to the earlier graphs, it's those lines. So these lines that we see here, where we've got the intensity as a function of wavelength, this was the big success that Max Planck came up with. You may have heard the Max Planck Institutes. There's a whole series of national labs in Germany that are all called the Max Planck Institutes, kind of like the Ernest Lawrence National Labs here in Berkeley and Oakland. See if we can catch up with where we are here. Okay, so that's the formula that Planck came up with, and by matching that formula to the data that was collected in laboratories, researchers were able to establish a value of Planck's constant, 6.626, something, something, something. It's in your book, in that front cover. 10 to the minus 34 joules times seconds, and that's in standard units. Okay, and then I just pointed out at the time, how did people used to do fitting? Well, you had instruments that were analog, and you read those analog instruments, and you got out paper and pencil and your slide rule and some graph paper, and were able to determine these values. There were no electronic calculators to work from. And here's this one more time too. I think this is a good comparison conceptually to think about. What's the difference between a container filled with gas molecules versus a container filled with photons. If I take a container with a bunch of gas molecules inside, there are photons in there also. So these formulas that we've come up with will tell us if I got a container and the material's here at a certain temperature, there's going to be some distribution of photons. I could take out all the gas molecules, the container will still be filled with those photons. Okay, the photons will still continue to be radiated into that volume and absorbed by the inner surface. Radiated, absorbed, it reaches some kind of an equilibrium. Okay, that's a good place to stop. So let's stop here, we'll take a 10-minute break, and then we'll come back and look at the rest of the chapter.